Good afternoon, good morning, good evening, depending on where you are on this fast forward planet, which is wrapped in so many layers of turbulent change. I stopped listing them. This show started back during the pandemic and continues because my goal here, this is Andy Revkin talking to you from down East Maine. My goal is to cut through complexity through conversation and some bits and pieces. It's a journey. It's not like we answer questions in one show. Today, we're going to talk about an issue I've been grappling with for a long time as a journalist, and my guests have been grappling with for years as scientists. It's how to understand patterns of tough weather, severe weather, winter in the wintertime in the context of human-driven global warming, which is this forcing on the global system. It's hard sometimes to sift out how it affects both precipitation and temperature. Temperature has gotten a little clearer. If you have a heat wave, the duration and or intensity of that heat wave is fairly much easier to distinguish scientifically than when you get into precipitation, particularly because the world is a very swirly place. So here we have Matthew Barlow at the top of your screen at the University of Massachusetts in Lowell. The last time he was on this show, I don't know if you remember, Matt, but your cell phone was doing a tornado alert.
I do remember that. Yeah, I was thinking of that right before I logged on,
That
actually.
was that was a first for me. We were talking about fragile states and disaster preparedness, and there was this that was interesting. And here we have Eric Osterberg, who's a professor at Dartmouth, studying climate with a particular focus on the dynamics we're trying to understand, and Jacob Chalif, who's a grad student at Dartmouth, who I intersected with a long time ago when I was teaching a summer course for the New York Times for pre-collegiate students. And you're way beyond that now. So that was easily 10 years ago. Oh, and I think we just lost Eric, but he'll come back on, I'm sure.
Yeah, I
So,
think that's about 10 years ago. Eric's getting an echo. He'll be back on in a minute.
oh yeah, okay. So he's going to come back. So just because he's off for a second, why don't we start with Matthew Barlow? And I want to just sort of get at what drove me to dive back into this, which was in part there was the usual kind of tweet from our fearless leader the other day: cold weather, global warming, bullshit, and that elicited a lot of responses from well-meaning progressives about no, no, global warming, you idiot, and what was lost there immediately was well, it followed a pattern that I've seen too much, where you have this, you have you're arguing from the edges of an issue. And so I started poking around, and I found the Dartmouth study. And here's Eric again. Eric, I was just talking about how Trump's tweet, in a way, led to this,
Hmm.
because I was poking around to see what the recent work has been on global warming and winter weather in North America. And your work at Dartmouth with Jacob came up. And so now that we have you back on, let's start with Dartmouth, because just trying to take this in sequence. And what, you know, maybe just Eric, just talk. What's been your work? What's your overall
Yeah.
portfolio when you think about climate change and severe weather?
Yeah, so I was, as a scientist, kind of born and raised as a polar scientist, focusing mostly on ice cores. And so that's what I did my PhD on, going to like Greenland, Antarctica, and Alaska, collecting ice cores. And I was really interested in sort of the last couple thousand years as we've transitioned from a natural climate state to this human-dominated climate state. And then beginning around 2014, 2012, 13, 14, or in that around there, started really getting interested in what was happening in my own backyard in New Hampshire and in northern New England in general, with the flooding that we were seeing, the extreme rainfall, and starting to ask some basic questions like, we're hearing that climate change is increasing, like extreme rainfall, extreme storms in this area. Like, is that true? And if so, like, what kinds of storms, what seasons, like, since when, right? Like, trying to
Right.
understand the details of that. And so started really digging into that with some grad students and coming up with some really interesting findings about like basically every type of storm that we get in the Northeast is actually, dropping more rain than it used to when they're sort of on the heavier side of things. And that's what really brought me to the jet stream, because around that same time, there was this really interesting scientific debate going on about how is climate change affecting the jet stream. And particularly where we live in the Northeast, like the jet stream is a massive part of our weather, right? Like it really determines our temperature and particularly like storm tracks and if we get whacked with a particular storm and how big that storm is. And so as we were thinking about extreme storms, it was natural to think about the jet stream and this larger debate about climate change in the jet stream. And so that sort of eventually led to Jacob's work and thinking about what's happening in the jet stream in different seasons. And one of the things we'll talk about is maybe it's not the same thing in the winter as it is in the summer, for example.
Right. Jacob, maybe briefly, you're the youngest here by far. How did you get sucked into this vortex of polar science, to abuse a term?
Yeah, basically Eric mentioned it. I was in a college class with Eric thinking about climate dynamics, and Eric brought up this idea of the jet stream, and it's a very active debate in the literature on how the jet stream is changing with climate change. And one of the things that Eric mentioned is that people in our group or other people here at Dartmouth have studied the jet stream going back to, I think, 2018, maybe earlier. But a guy named Trevor Partridge here published a paper in 2018 that potentially identified this period in the mid 20th century that had a heightened period of jet stream waviness. And there was this apparent contradiction between this heightened jet stream waviness from the 1950s through 70s or even 80s, and then also heightened jet stream waviness in the 90s to 2010s. And like maybe both were true, but trying to think about putting some long-term context on this, recent increase in jet stream waviness kind of caught my attention at first, and that's how I first got involved. And since then, I've kind of followed Eric's path and done a lot of polar science in Antarctica and Alaska as well.
Yeah, I saw the Antarctic work. We'll have to do a whole separate session on that. That's really exciting.
Yeah.
So the jet stream is an interesting question because so much of our observational capacity has evolved tremendously, expanded tremendously just in the last half century. And how did you, part of your work, as far as I could understand, the paper that came out last year was extending that record, or at least understanding backwards in time into the pre-modern measurement effort, right back to 1901, I think, if that's correct. So maybe you could both talk about that. And Matt, we're going to get to you in a second on these same questions.
Yeah. So we have really phenomenal measurements of our climate going back to about 1979. This is kind of a golden year in climate science. You see it all the time because it's when our weather satellites came online. So beginning in 1979, we have really good data on how the jet stream, as well as many other parts of our atmosphere, behaved. Where we entered the pictures, there's a hypothesis that Arctic amplification, or the amplified warming of the Arctic is warming faster than anywhere else on Earth, could cause an increase in jet stream waviness in the mid-latitudes where we live. Well, Arctic amplification took off in the mid-90s. And if we only have good satellite observations back to 1979, that leaves about 15 years for a pre-Arctic amplification baseline. And climatologists like to use on the order of 30-year baselines because there's a lot of higher frequency noise that can kind of muddy a shorter term signal.
Right.
And so to extend the record back before 1979, we relied on these wonderful data sets called reanalysis models. Reanalysis models are basically weather models that are fine-tuned to reconstruct surface temperature and pressure observations and other types of weather observations that we experience. And so they're run back in time, and they reconstruct not just the atmosphere on the surface based on the observations, but throughout the entire atmospheric column. So it tells us not just temperature on the ground, but also what are the upper atmospheric dynamics leading to those weather systems like the jet stream. You have to be a little bit careful using them when you go before 1979 because they rely on surface weather station observations. And the farther back in time you go, the less and less of these surface weather stations we have. And especially if you go to places that are undersampled, like many parts of the global south, they have particularly poor data coverage. So to get around that for our study, we focused in on North America because the United States has really solid weather station coverage throughout the 20th century. And we used, I think it was 5 different reanalysis models, each of which ingest different or distinct sets of weather observations into distinct physical models. And the idea there is if they all agree with each other, there's a good chance the signal we're seeing is real. Putting that all together, what we found is exactly what's on the screen here, which is that this highlighted area on the right, this is the purple increase in jet stream waviness that's been associated with Arctic amplification. But if you go back in time to the left, there were several periods throughout the 20th century in the 60s, late 70s through 80s, even in the 40s, they experienced regimes that were as wavy, if not wavier, than the jet stream we experienced recently.
Right.
Yeah.
So that says several important things to me. One thing I always tell my journalism colleagues, some of whom are newer on the beat than I am, is anytime when someone says uses a word like unprecedented, the first thing is to say since when, meaning what's your time scale, and actually I do a series of shows on what I call watchwords, words to sort of when you see a word in a headline or in a paper, that it's a word that should elicit some response. And for unprecedented or extreme, it's like even extreme. The definition of the word extreme is a function of time, extreme frequency or the like. And you only understand that if you look further back. So Matt, I want to bring you in now here before we go further and talk a little bit about you've studied climate variability and change in many parts of the world, and you've worked with Judah Cohen and others on who couldn't get on the show today on these same kinds of questions, but with a little bit of a different set of tools and the like. Maybe we could talk about your work a little bit.
Yeah, so I come at this from, I think, the sort of broad perspective of just trying to understand extremes. You know, what makes it hot, what makes it cold, what makes it wet, what makes it dry. And you know, I would have been perfectly happy to just focus on just that question, but of course, climate change skews everything. So then you have to worry about how climate change is you know, changing the things that you're trying to study. So we look at all of those things, but cold, I think, is particularly interesting because it's a little counterintuitive here. You know, as you said with the tweet that sort of started this all off, you know, I think it's important to realize that we're not done with winter yet. I mean, I think, you know, there are some very conclusive things we can say, and one is that we're getting fewer cold events. I think that's quite clear, but that doesn't mean no cold events, and that doesn't necessarily tell us how strong those cold events you know, will be when they occur, which I think is a really interesting question. And just to bring in the impact side of it, I think another piece of context here is that as we're hopefully, you know, doing a green transition away from fossil fuel heating in the winter, part of that is that we're electrifying heating. So we're putting a lot more strain on the grid when it's cold in winter, which I think really makes these cold events extra important as we're, you know, kind of hopefully trending towards a different environment in terms of the electrical grid. So that's where I come from, I think, from that broader extremes perspective. And then with the cold, one thing we've been really interested in, as you said, especially with Judah, is the connection to the stratosphere. There's I think, a really growing appreciation over the last several years that what goes on in the stratosphere doesn't necessarily stay in the stratosphere. And there's under some conditions, a pretty strong link between the surface and what's going on, you know, more than 30 miles up in the atmosphere, where we have the stratospheric polar vortex. And polar vortex is a phrase that gets used in a couple of different ways, but here, I'm thinking of the winds that are way high up in the atmosphere. So there's at this point a pretty well-established link between the stratosphere and these kind of cold events at the surface. Where I think the science is interesting right now is exactly how that link works and how much it's changing or not changing with climate change. And our hypothesis is that as things warm, it changes the land surface conditions in the fall, and that has the potential to disrupt the polar vortex during the winter. So that's the angle that we're interested in is, what are the links to the stratosphere, and are those changing over time?
I'm showing actually there's still some information on the United States government website about this, despite the best efforts of the Trump administration to expunge any mention of things related to climate change. This is at climate.gov. For those who want to learn more, just Google for understanding the polar vortex and climate.gov. And this we still, we'll dig in a little bit more on the global warming component here, because the work that in the Dartmouth et al. Study really does show that you've got more variability with the similar extent of conditions that we have now back through at least a big chunk of the 20th century. Had you been able to look at their work, and you have any thoughts in general about it?
I mean, I don't know that I fully digested it yet, but I really appreciate looking back to 1900. I think that's a really, it's incredibly valuable to put kind of the recent variability in that much larger context. So I really think that's fantastic. And the link to the warming hole as well is a really nice outcome of that research. So I thought it was super interesting to see those earlier peaks in waviness. Now I have to admit, I'm also very jealous because those reconstructions pre-1950 rely heavily on surface data, and our confidence in the reconstruction kind of goes down as you go up in the atmosphere. So
yeah, sure.
Yeah, it's a little I think the information in the stratosphere is probably more not as well defined in that earlier data, but I really do like this approach, and the wavy jet hypothesis has certainly been on a lot of people's mind, and there's been a lot of back and forth on it. So I think that this is really kind of a nice long-term perspective on that. What we haven't really done is try to link jet waviness to the stratosphere. So that's a really interesting thing. And I was actually thinking this afternoon, I should ask you guys if I can borrow your index and take a look at that, because I think it's a really interesting question, and not one that we've looked at. We certainly see an influence on the jet, which you would have to, I think, if the stratosphere and the troposphere are linked. You have to have some intermediate signal on the way up and down. But I'm not sure whether it's linked to jet waviness or not. So I think that's a really interesting question.
Any thoughts from Eric and Jacob on that?
First of all, happy to love to work with you thinking about stratosphere further back in time. I mean, it's interesting to think about. I appreciate the deeper context, right? And I think that part of that comes from the sort of the fact that I come out of a paleoclimate world where that's our whole thing, right? Is trying to get longer context to understand how the atmosphere actually works, what's actually going on, and I think there are real limitations, there are real challenges to going back further and further in time, but for some of these questions, right, we actually had pretty good data. And again, the way what I really appreciated about Jacob's study, and to be clear, he did all the work here. What I really appreciated about it was he hit it with every good data set that's out there, and to compare the results and see like what's consistent here, what's consistently coming through these different data sets, these different models. And as he suggested, like that increases your confidence, right? If you're seeing the same story coming from different data sets, even though there is some uncertainty as you go further back.
We didn't talk. The paper actually centers a little bit on that warming hole that we were talking about a minute ago, but we didn't actually get into that at all. Can you talk about that a little bit? Maybe Jacob first.
Yeah. So the warming hole is this period of cooling in the southeast U.S. I should specify the U.S. warming hole. There's another one in the North Atlantic, but the U.S. warming hole is this cooling phenomenon in the late 20th century. And so in the late 90s, if people plotted up 20th century temperature trends, they found that there was this kind of big blue blob in the southeast US that experienced cooling, unlike the rest of the US. And there have been a lot of different hypotheses put forward for why the southeast US cooled in the mid to late 20th century. Where Trevor Partridge came in, who was the one that published his paper in 2018, is he identified that the causes of the warming hole in the summer might be distinct from the causes and spatial distribution of the warming hole in the winter. And so where we came in is we had this hypothesis that the warming hole in the winter, this cooling in the winter, could be linked to increases in these troughs in the jet stream that allow an excursion of cold Arctic air to escape south. But when we dug into it, there really weren't that many or really any papers that have studied the jet stream pre-1979, which limited how much we could say about that. So one of our goals was to see to what extent is the warming hole actually, in the winter anyway, related to or even caused by changes in jet stream waviness. And so getting into the weeds a little bit, we did this kind of like machine learning-esque approach to deconvolute different causes of the warming hole. We did find the jet stream, at least changes in jet stream waviness and the frequency of waves in the 60s, 70s, and 80s were linked to about 2/3 of the cooling signal that we experienced on the ground.
One of the things that's there's a parallel here between the warming hole and the kinds of storms that we just had, a few days ago here with the president's social media post, is that both of them tend to raise these questions about like, hey, what happened to global warming, right? And that the observation that the Southeast United States has not warmed as much as the rest of the world, at least during these few decades in the mid to late 20th century, that's real, right? And it is actually a really interesting opportunity. I mean, I kind of appreciate the president saying, like, please explain. Like, it's a really cool opportunity for those of us to try and understand this better. And like, can we explain this, right?
Right.
And what was really neat about Trevor's work first was saying, well, hold on here. Actually, it's probably different what's happening in the summertime versus what's happening in the wintertime. It looks different. It's in a different place, slightly different timing. And then Jacob came along and said, all right, well, let's dig into what's happening in the winter. And that's what led us to the jet stream and thinking about, well, hold on, the warming hole's before 1979. So we're going to have to figure out a way to look further back in time. And that's how we ended up where that paper did, looking at the whole 20th century.
Oh, that's so interesting. And I wanted to then, as you started to do it, to make the link between, not necessarily the link, but to examine if there's anything related to storm patterns that can sync up or that syncs with what's understood about those patterns in the high level dynamics of the atmosphere. And I know, Matthew, you've been involved with this too. It's actually mentioned in this really good piece you did with Judah in the conversation. You talked about Michael Mann's paper as well on nor'easters. I mean, the reason we're having this conversation is because of an epic multi-day storm that where I live in down East Maine, actually where most of you live, was at least in part a nor'easter. So how does that, the thing that affects people is weather. Like my son in Nashville, who still had big chunks of Nashville have no power because of the ice storm.
Yeah, I mean, I guess I would frame that as a question in some sense. I mean, I think it was the eighth biggest snowstorm in Boston's history. I mean, before I frame it form of a question, I think it's probably worth acknowledging that extreme events are by definition rare, and
Right.
so it's really hard. Uh, when that's one of the nice things about these really taking the longer view is you can get a better sense of what's going on. Because if you're talking about a relatively small number of events, even if they're distributed randomly, it's going to look like there's a pattern. So I just want to start by acknowledging that there's a role of just chance, of randomness in a lot of these events. That said, I mean, like you mentioned, Mike Mann and his colleagues had a paper in the last year, I guess, in the Proceedings of the National Academy, and they found that nor'easters, these strong winter storms, that the most intense of the intense nor'easters are becoming more intense, and I think that's a pattern we're starting to see in a lot of extremes. That if you look at the average event, you see something different, does not necessarily trend in the same direction even as what's happening to the most extreme events. So, and I think that has a lot to do with increased moisture in the atmosphere, which we could also talk about. But I guess my question is with the wavy index, is that more capturing median events or extremes?
I think it's a great question. I guess it would. The way I think about it is it captures the frequency of like dynamic regimes that we would classify as a jet stream wave as a whole. We could talk more offline about this, but there are ways of using this to also look directly at extremes versus medians versus like I don't know, mild waves, I guess. But the way I think about it is it captures just kind of broad scale median, at least as we did it in this paper, like waviness behavior.
Yeah, I guess I'm really curious about that, and we should talk about it offline, I think, rather than fully getting into the weeds here. But because we are seeing trends in intensity, certainly in precipitation intensity, but in some metrics of storm intensity. And I was sort of wondering how that would line up with the trends in waviness that you guys saw.
Yeah. I mean, the way I think, go ahead, Eric.
No, I don't want to interrupt.
I was just going to say, I think it's a really interesting question. And, my thinking on this has evolved. Maybe it's right, evolving in a good way or in a bad way. I don't know. But as scientists, right, we're constantly questioning our understanding of these things. And I think where I was in maybe the late teens, as we were really thinking about the jet stream, was like that the jet stream was this critical way of linking climate change writ large, polar Arctic amplification in particular, and weather that actually affects people, right? To your point, Andy, like these are the storms that actually impact people. And to me, like the jet stream was this sort of perfect connection between it, because that's a challenge that climate scientists often have, is like, well, wait a minute, like 2 degree C mean annual temperature warming, like what does that even mean? Like the storms are really what we're talking about here in terms of those impacts that everybody can understand. And I am focused now personally less on the jet stream and more on what you said just a moment ago, which is the amount of moisture in the atmosphere, right? Like that is in my current way of thinking about it, like that is the thing that connects all of this together, right? And what's beautiful about it is that it's like the most basic physical principle of the atmosphere, right? As the atmosphere warms, it can hold more moisture, right? Like we talk about it, in the weeds as like Clausius-Clapeyron relationship, but this relationship as the atmosphere warms up, it can hold more moisture, and it's not a linear relationship, right? It's an exponential relationship. So small changes in temperature, small warming, creates a really large increase in the amount of moisture in the atmosphere, and we started coming to this like really simple way of thinking about it because as I mentioned in the beginning, when we looked, we actually had a grad student who said, okay, if we look at these extreme storms in New England, there's like 3 different kinds of storms that tend to be like extreme rainfall events, right? There's nor'easters like we're talking about. There's those summer thunderstorms. And then there's like tropical systems that make their way all the way up here, right? Hurricanes, tropical storms that end up sort of dying down, but they're still tropical systems.
Yeah.
And what we found is that all 3 of those things dumping more water than they used to, right? And again, like the research that other people have been putting out about how, like that paper you were just talking about from Mann's group, that the nor'easters seem to be dumping more precipitation, dumping more snow. There's other papers showing that in the Northeast going back to 2018. And like that relationship between water vapor isn't just about what's coming out of the atmosphere as precipitation. It also fuels these storms, right? We know as meteorologists that like when that water vapor turns into snow and rain in the atmosphere, when it condenses, it's releasing energy and it makes the storms more intense. So it's like this beautiful unifying way of thinking about it that is different from the jet stream in my mind, right? It's almost simpler in a lot of ways.
Yeah, I think the complexity that at least I struggle with a little bit. I entirely agree with you, and I think also that's where we're on the sort of strongest ground.
Yeah,
it's just much simpler, but especially with nor'easters, you know, the meridional temperature gradient's a big player. But what seems complicated to me is that as you get Arctic amplification, you're reducing the low-level meridional gradient. But as you warm the tropics, you're actually increasing the upper level, the sort
stratosphere.
the top of the jet. So there's, and I think this is something that Paul Williams talks about with turbulence, increases in turbulence, is that the effect of warming on the low level part of the jet is actually opposite to the effect of warming on the upper level part of the jet. So you're probably somewhat decreasing the main source of energy for these winter storms, but you're also changing the stability, and you're definitely increasing a secondary source of energy. So it does seem quite complicated to me to figure out, especially the temperature piece, because the moisture piece, I agree, is completely clear. But whether it falls as rain or snow or ice, unfortunately, is a really tricky question, I think, with sort of a lot of impacts to it.
So I want to take this to, because Eric, you mentioned your interest in paleo work and how it related to long-term records for the Northeast. You brought me back to 2002 and a paper by Norin Bierman and others.
Yes.
Which I think about all the time.
Yeah, it's a great paper.
I wrote about it in the New York Times at the time.
Yeah.
I've stayed in touch with Paul Bierman and others. And so far, despite this being 23 years ago, I don't know what it is, nothing has undercut these findings. And what they did, they cored the lakes around the Northeast, and they were looking for patterns of storminess that were articulated by layers of sort of gravel. And so you get mud, gravel, and that would indicate there was a violent scouring storm in the hills of Vermont and the like. And one of the conclusions was that I highlighted here, I've highlighted many times. Basically, they say, watch out if you're looking for a signal of global warming, because this pattern appears to be in its reviving toward having even more of this storminess than there was in the 20th century. And it says, because climate synopses compiled from instrumental records can't distinguish natural from anthropogenic effects, detected increases in contemporary storminess may not be a reliable indicator of human-induced climate change. So, and I wrote about it at the time. I wrote about it in 2009 in a piece on weird weather in a warming world. And obviously right now we're talking about winter weather. This was the storm of record here was a late season 1927, I think it was, hurricane, like the Helene kind of thing that got into Vermont. Was devastating. So just thinking about that stepping back from the winter question to the confidence question related to global warming, and this is multi-thousand year time scale, so it was very sobering to me as a journalist when I did that work. And there were later papers I did on paleotempestology. I mean, stories that were very sobering as well. Does that perpetually affect the confidence level in talking about climate change and these events that are most consequential for people?
It's a really cool question. I honestly, I know this paper well, and I love this paper. It honestly doesn't really come into the way I think about looking at these records over the last 120 years. I mean, I've spent a lot of my career looking at what we call the Holocene, right? The last 10,000 years since we came out of the last ice age. And we have ice core records, say from Alaska, that show, some really interesting stormy times, maybe 4,000 years ago and such, that are really difficult for us to understand because we get these little snapshots and we maybe see this one record, right? Like there are not many records of storminess from Alaska that go back 4,000 years. So we get like one or two of them. And it's tough to really fully understand what you're seeing, except to say like, wow, like there's a lot more for us to understand here. But I think going back to what we were talking about, like this relationship between, say, temperature and the amount of moisture in the atmosphere, and therefore how much a storm is raining or snowing, right? Like that is such a fundamental relationship that we understand really, really well. That doesn't give me pause to say like, hey, this is going on. Like we are seeing this because we know how much it's been warming. We have actually really good data about how storms have been changing and rainfall and snowfall has been changing. Rainfall more than snowfall, I would say.
Yeah.
And so it's in my mind, even as a paleoclimate scientist who does like modern stuff too, like they're almost in separate compartments in my mind, if that makes any sense.
Matt, what do you think about that?
Yeah, I think I'm in agreement with that. I sort of separate it in some sense, the different pieces of the problem, which I think is one reason why I really appreciate Eric's emphasis on the precipitation intensity, the increased moisture part. That's really one of the oldest predictions of global warming is increased moisture and an enhanced hydrologic cycle. I mean, the very first climate model, Suki Manabe's model showed that, in the 60s. So, and we've understood the physics behind it probably for more than 150 years. So a warmer world that has a warmer surface, a warmer ocean, and a warmer atmosphere, we understand the physics of that. We've predicted it in models before it was observed, and then we've observed it. So I think that's rock solid science, that sort of increase. So in my mind, I sort of separate that from, okay, so that's kind of the thermodynamic piece or the moisture piece of it. These dynamical pieces, which I think are really interesting and really important, to me are in a different category of confidence. So that's how I think about it. So when I think about the connection to the stratosphere, I think the connection to the stratosphere is pretty solid, although even current models struggle to resolve some aspects of that. And I think its possible connection to climate change is provocative and interesting and important to study, but it's in a different category of confidence for me than these basic aspects of more intense precipitation and greater fuel for storms.
Yeah, my takeaway when I think about the sort of long time scale work, whether it's paleo or historical and global warming, derives from the risk formula for what people do. And risk is hazard, exposure, and vulnerability. And I think what I see too often is people get caught up in the idea, for example, adaptation is thought of as adaptation to climate change, as opposed as vulnerability reduction to climate hazards, some of which will be tangled forever in terms of what CO2 driven warming will do. and some of which are more clear cut, like heat. And so if you start with sort of the risk question, how do we reduce risk? One, you can modulate the hazard, which is partially through CO2 reduction. Maybe geoengineering if that ever happens, but
No.
that's just no. I know I've done sessions on
Please
that.
no.
No. I know we're not going to get into that today. Or vulnerability and exposure. Where you build, how you build. Here, or how you deal with poverty here in the Northeast. As you know, poor people. There's a lot of energy poverty. Yeah. I have neighbors. There's a nonprofit wood bank here just up the road from me where people contribute work to split firewood for families who are not going to make it through the winter, and maybe they don't have a generator like we're lucky to have. And so cold is in the system. It's getting less cold, but that's not for Maine or New Hampshire or even parts of Massachusetts. That's not relevant if you're in a cold snap. And thinking about ice storms and those vulnerabilities, getting at that stuff and not getting caught up in debates like, is Trump right or wrong? That's at a level that is a distraction ultimately from the reality that we're vulnerable.
Yeah.
And I'm a total science geek. I love this conversation, and it does relate to both understanding variability and understanding change relate to the risk we face around the world from climate hazards.
And when I think about vulnerability, I think particularly as physical scientists, which I am, I guess we all are here, right? Like we think about a lot of these physical ways of reducing vulnerability, right? If you want to talk about flooding, like elevating houses or adding, particular flood protections or bioswales or whatever. More and more, I'm really focused on these social vulnerabilities and the ways that we can increase our social resilience, right? And seeing it as this like foundation for anything else we might do. And you can see these really amazing examples of this when we have events like this storm from last week, right? Neighbors helping neighbors, neighbors being aware of which neighbors are most vulnerable, which neighbors, if the power goes out, they're at real risk, right? And then making sure they're actually going and checking on them and thinking about all the different layers from the community level to the state level to maybe the federal level to promote those kinds of social resilience measures as a foundation for any of these other physical measures we might take to increase resilience and physical measures we might take to reduce the risk through mitigation, right? Reducing CO2 or whatever else.
Yeah, I think that's a great point because you can improve your resilience while improving other aspects of your life and making things better overall. I think the more that folks are connected to community, that has a lot of positive aspects, including mental health and physical health and response to all sorts of disasters. So I think that sometimes people look at climate solutions and they think, oh, this is going to cost me. But maybe it'll be cheaper. Maybe your energy, if you have network geothermal or something like that, maybe your energy will be cheaper and more reliable and also more resilient to climate change. But while we're on the topic of community, I expect I'm probably preaching to the choir, but one of the key aspects of our resilience as a society is the federal government. Really the foundation of our ability to monitor, to predict, to understand, to respond to these kind of events comes through the federal government. It comes through federally funded observations. It comes through federal employees at the Weather Service, at NOAA, comes through federal labs, which are, under threat. I think we've lost more than 10,000 PhDs at the federal level over the last year. I think that just came out. So I would just sort of highlight the kind of federal infrastructure that I think is invisible to most people, but really is the foundation for a lot of what we're talking about.
That's a great point.
Yeah, I agree completely. There was one thing, I'm going to show this just because you're taking me back again. Several years ago, under Biden, the government launched a website called heat.gov.
Yeah.
which was basically a go-to place for heat. And at the time, I wrote a piece saying this is great, but there also should be cold.gov.
Mm.
And because I did a really illuminating webcast several years ago with folks about vulnerability reduction, and there was a University of Michigan and Michigan State study showing that many cities around that sort of heartland part of America that can be really hot in the summer and really cold in the winter, that the same strategies and policies can cut the both at the same time. Well, weatherizing a house of a poor person is limiting their risk to cold and heat. And so I did a post earlier this year. I know it was going nowhere, saying there's one thing Trump could do, given all of his destructive patterns, is maybe they could finally do a cold.gov and heat.gov. So this was a card I produced for that. The U.S. needs both. We need to be thinking about vulnerability reduction to extremes in the climate system. And so this is my call out to anybody. We need cold.gov to go with heat.gov.
And I think these kind of weather events are a great way to communicate with people about climate change. I think a lot of people are interested in the weather because it affects them. That's primarily the way we experience climate effects, I think, is through weather, but also just people are interested in it. And to go back to Eric's point about community, I think, I forget the exact statistic, but most people are very concerned about climate change, but most people don't think other people are. So the more there's discussion of it, and I think weather is a great way to bring in that discussion, the more people will realize that I think we're all would like to head in the same, or most of us would like to head in the same direction.
Yeah, for sure. Jacob, you're of the generation that will inherit a lot more of this challenge than the three of us. What do you think about this question of the policy end here, and what scientists can and should do to drive smarter, help inspire or drive smarter approaches to this kind of weather?
I mean, I agree with everything that Eric and Matt have said. The lack of federal response to climate in the past year has been devastating. But one thing as a scientist that I do is, and the reason I study past climate is, I personally struggle to put climate change in any sort of baseline. I struggle to put last winter in the context of winters that I grew up. I grew up outside New York City. We used to get snow every winter. This winter has been the first time that, where I grew up has gotten snow in several years now. That's a major change, but I think that it's often hard to put long-term, multi-decadal changes in climate in that context. And so one thing I do as a scientist is I try to, kind of going back to this study, put this long-term perspective on climate, remind us how we got here. Because even if we as people struggle to think back to, say, winters of our childhood, that doesn't mean that systems we rely on, like agriculture and ecosystems, snowmelt, rivers, drought, etc., all of that, we rely on those systems. They know the change that they were doing, even if we struggle to remember. And so that's something as a scientist that I'm trying to do. But also doing things like this, I think that we need to, as climate scientists have done for decades, get this message out there and take advantage of when people are interested in listening to get this message out.
And I have one more question, and we're getting toward the end, but not there yet. One more question comes to mind. What we're talking about here is the different chunks of the climate science community talking to each other more, if possible. Paleo, observation, and modeling, and now machine learning. How much crosstalk is there across geography? This is something I started to focus on a while ago on that long time scale, sort of Holocene early level. There was a project to look across around the North America, the Northern Hemisphere, at data sets on climate and ecology. Faces, I think, can't remember what it's called. And I on this issue, how much do the sort of atmospheric river people out west talk to the nor'easter people in terms of the dynamics they're looking at and over time scales and the like. Does that happen much?
Yeah, yeah, definitely.
Good.
Yeah.
I'm glad.
Those atmospheric river folks out west, like they got it good, right? Like they get those really cool river events, right? We get the nor'easters, they get the rivers. It's actually funny when you see terms, Matt, you mentioned like how polar vortex has become this term that's used a lot more. It's been a meteorological term for a long time, but now it's used in different ways in the public.
Yeah.
And like atmospheric river is, when I was doing research out in Alaska as a grad student with another scientist, like it was Pineapple Express, right? That's what they were called out there. And now we've got this atmospheric river. And then we'll be at a conference and I saw somebody like investigating atmospheric rivers on the East Coast. And I was like, ooh, there we go. Right. Like we're having this cross-pollination of science. So, we're the at least actually, I wouldn't just say US, like the international climate community of scientists is a really well-functioning, well-collaborating group. I mean, we spend a lot of time collaborating with folks at other institutions and folks in other countries. I know there was this discussion of Greenland recently, which for those of us who work in Greenland was just devastating, right? Because we've got colleagues who are both Danish colleagues and our Greenlandic colleagues, and that's not how we as scientists interact with one another, and not how we would like our governments to interact with one another. So, I think there's quite a bit of cross-pollination, at least from my perspective. I don't know how Matt and Jacob feel.
Yeah, I would say the last set of IPCC reports, the sixth assessment report, now they're starting the seventh, but the sixth assessment report, I think they made sure there was a paleo person on every chapter.
That's
so
great.
I think that there was a sort of a recognition that was a particular tie that needed to be strengthened. Now, whether our paleo colleagues felt adequately represented or just singled out by that, I wouldn't care to to say. But I think that there was has been over the last, from my perspective, at least a decade or so, I think a real emphasis on grappling more with the paleo and the long-term record for all the reasons that Eric and Jacob talked about today, and I think that's really important. I'll just shout out what I think is one of the interesting things that I suspect we'll be hearing more about is paleo records of fire in the Northeast, to try to get a sense, because we've changed our forest, we've changed our fire management so heavily, it's hard to get a sense of what the baseline counterfactual risk of fire might be, which I think is a really big question right now in the Northeast.
Absolutely, yeah.
The one thing I thought we should get to that I forgot is warm seas, warm oceans, and how that relates to this. Matthew, this was in the conversation piece, and I'm sure it's related to the other work too. Just maybe we could talk about that as relates to that. Obviously, that's a source of moisture, but dynamics of the circulation as well.
Yeah, I mean, again, working from most certain to least certain, it's a source of moisture. A warmer ocean can evaporate more, so you're, putting more moisture into the atmosphere. It can, under the right conditions, also sort of enhance the contrast, the temperature, low-level temperature contrast between a cold continent and an extra warm ocean. And here in the Northeast, the oceans are warming. It's one of the fastest warming places on the Earth, right off the coast. And then they have these kind of big, complicated, less certain impacts on the global sort of circulation of the atmosphere. And I think that's another one of those questions that we're really wrestling with right now is if you change the patterns of where it's warming faster and less fast over the ocean, how does that change circulation systems? How does that maybe change the pathways of storms and so on? And I think that's a complex question.
And then there's the Arctic, the sea ice and snow fields in Siberia, which Judah Cohen has done a lot of work on, which I focused on a lot, having gone to the North Pole in 2003 and gone to other places in the Arctic. it's all connected.
Well, you mean you can look at this storm right now, the one we just had,
Yeah.
right? And the Gulf of Mexico, I was just looking recently, is the warmest it's been on record, and that's where a lot of the moisture is coming from, coming up the east coast of the eastern seaboard of the U.S. Right, the Gulf Stream waters there are also extremely unusually warm compared to what they've been in the past. And that's the fuel for these storms. And actually, we got another one, right, that the models are showing for Saturday night.
We are looking very carefully here in Maine.
Yeah, and
Once
right
again.
now, I mean, because North Carolina has snow from this last storm, that's enhancing this land-sea temperature difference that Matt's talking about, right? So cold land, really warm ocean right offshore, right next to each other. That's what spins these nor'easters up. And so you can look in the models right now for, Friday, Saturday night, and Sunday. And it's just a sort of like weak little system comes down, and then it hits that temperature contrast in North Carolina, and just boom, just bomb cyclone is what we call it, right? It just incredibly intensifies very quickly, and we'll be watching to see where it goes. It could go out to sea, could go up the coast like the last one. We really don't know yet, but maybe in a couple of days we'll know better.
Yeah, I'm showing one of the illustrations from Matt Barlow and Judah Cohen's piece too. This was the circulation for the storm that struck a week or so ago. Yeah, we'll be paying. Well, we should all be paying attention to forecasts and also to the federal resources that underpin all the forecasts. You have all these voices out there now on the internet. When they cite the models, they're citing federally financed systems, both here and internationally, that give us together the improved skill to understand what's coming, to reduce vulnerability, and then the climate models to understand better the long-term changes that we're exerting on the system. This has been a great conversation. Maybe we can reconvene down the line, and I hope you do have that conversation to share data and ideas. I'm always glad when I bring people together who haven't intersected before, except in the literature. And thank you all for being part of Sustain What today.
Thanks very much for the conversation.
And anyone who's watching, just if you want to get in touch, just there's that distracting scrolling bar at the bottom is how to get in touch with more information. This will be archived right away, and anyone can share the version of the video that you're watching. This is Andy Revkin from very snowy coastal Maine. Expecting more before this winter is out, and it was below zero here this morning. Our sump pump exit drain pipe froze, which was not fun. Yeah, so be prepared. I tell you, be prepared. Thank you, and hold on a second.